Okay, so now we will get into the flow part. Of compressible flow. Before we talked about compressible part, now we're going to get to this flow part. So this involves velocities. Right, so velocity information or duct area, etc. So fluid moving through some sort of conduit, how does the flow behave if it's compressible? So this is where the isentropic flow situations arise. And they arise because of simplifications of small, simple diagrams that we can draw. So in this compressible flow type problem, there are really three simplest cases we can have. There's this first one we're going to do, which involves situations that look like this, where you have, let's say, this is a wall for the flow, right? And I have gas moving in at some mass flow rate, right? We have to use mass flow rate now, or an m dot, because the density can change along the conduit. Okay, here's some center line. So for this situation, right, okay, notice here now, if this is the x coordinate, that area changes as a function of x for this type of a situation. Right, so the situations here is that dA dx is definitely not zero. And then assumptions also we can make is, right, that negligible heat transfer. So that's adiabatic. It's the adiabatic assumption. There's no heat transfer from the interior of the conduit to the outside, or vice versa. So any sort of heat flux from the outside to the inside, negligible. You say zero, but in reality nothing's ever zero, so you just say negligible. So I don't like saying equals zero. And then the other things that we have is sort of the isentropic part, and that's this idea that the viscosity of the fluid and the roughness of the walls are also about zero. So this is this isentropic property, or entropy change is effectively zero. So these are the measure of like losses that occur in the flow as it's happening. For gas, this is pretty much always satisfied because the viscosity of the air is pretty small. And then in smooth walls, is also like frictional effects. So if you have a smoothish wall, this is also satisfied. But the biggest change you have is the fact that the dA dx is not zero. It's non-negligible. Clearly, if you look at here, right, you have this changing area as the flow will progress. Right? This turns out to be one of the simplest problems we can solve. So one, right? And it's simple just from, if you just did the analysis, you would come up with what we'll do. Just these are the easiest way to go. The other ones are a bit more difficult. So this is the first case we'll study, right? What does this mean, adiabatic? And really what happens is there's some ranking to these things, but I'll do that next. Another type of simple flow problem that we could draw is a single straight pipe. Right now, right here again, we'll have insulated walls, a pipe. And remember, right, still have gas, an m dot, rho a v. Right, so same setup here now, only here, right, our assumptions change because now we know that dA dx is zero, effectively zero. If it's a rough wall, it could be different, but I'm saying really the total derivative is about zero. Same idea that effectively no heat transfer is happening, adiabatic still. But now this time, sort of the, what do you have? Not so greater than zero. So now this is where losses matter. So this is no longer isentropic. So sometimes losses matter in this case. So this could really, usually because, right, usually because with gas flows, this number is already fairly small. That one you don't really have much change off. So this scenario involves sort of like rough wall. Right, rough walls is really what exemplifies this type of thing. You have air flowing through a straight pipe, but the surface on the inside is like really rough. It could just be like, conduits all throughout your thing, or some sort of like sensors, etc., that make it an effective roughness that's definitely large. So you get losses involved in your flow, but you still retain this, and this helps you. You have to also consider the changing area. So we're sort of only selecting one of these things at a time. I imagine you can all guess what the other situation would be. Right? Okay, the other situation then is still a single straight pipe. Same scenario before. Once again. Right? Not much area change there. But now, you do have heat transfer through your single straight pipe in a compressible flow problem. But you couple that with, I still have smooth walls. Right? So the problem, you can't say it's isentropic because there's a change in heat right here, but this simplification, the viscous losses or your roughness losses are neglected, make this a contractible type problem. So those are the three cases. We're going to go over the first one that I drew about changing duct area because it just is always the first step for these types of flow problems. And they have special names too. Each of those problems has its own name. And really what happens is it's all about just ranking the relative magnitude of the effects, right? So for the first problem, right, it's an isentropic flow properties that we have. And it's really an ordering of happens, because if you have pressures or temperatures or flow variables, right, really what you're saying for this type of thing to be true is that the greatest effect that happens is the dA dx term. Even if there was heat transfer, if there was viscous losses, it's just that, right, in this situation, what matters most is right, that, right, this is a much larger effect than that Q or that, right? So this just matters more than the other ones. And the same thing is true for the other types of problems we had. It's just ranking their orders, right? So the isentropic is that situation. The other one I drew, that one has a name called Fano flow. So Fano flow is a situation where it's really the viscous or the roughness losses that matter most. So sort of like this matters more, like really much more, right, than the rest of that stuff. And so there's a name for that. And then that third one doesn't really have a name, but you end up producing these plots. So I think I gave it this name, Rayleigh lines. So I don't know if it's actually called this, but you end up looking at Rayleigh lines for the situation. And this is the case when the heat transfer in your flow matters a lot more than the rest of those properties. Okay. So it's just really a ranking for these simple problems. And that's true over all analysis you have to do as a first step, is just to select out situations where one thing is the most important thing more than all the rest of them. Because it's really hard to solve these types of problems where all these are kind of on the same order, right? This is super hard. Right? If all of these effects are kind of around the same order, if there's heat transfer and there's area changing and there's a lot of roughness happening, to really throw math at that, it's really not equipped to do it yet. But these still are helpful because what we end up doing is you can do something like this, right? So in this section of my analysis, you can model just this part of the flow as the isentropic part. And then once it can diverges next to like a steady, right, to a constant area duct, and let's say it's rough, and here, you just link together the analysis with this Fano and Rayleigh relationships in this constant area duct. So here it's 0, here, not 0. And the Rayleigh, right, for great heat transfers, that's involved with like really rocket nozzles because you have enormous amounts of heat transfer happening. And for Fano type things, it's like it's hard to find really applicable problems, but they are there. Just you have like really rough walls. Even a combination of both these could be on there. You can even superimpose the two analyses in a really rough approximation. So you do your isentropic relationships for changing airflow, and then you could even like separate the analysis of these two things by doing a Fano relationship and just superimposing the other simple case. That the bulk effects is a Fano plus the Rayleigh effects. Now keep in mind, this is like wrong, right? Right? It's definitely wrong to just superimpose these two effects, but it could get you close enough to see where you maybe would lie. In reality, if you wanted to have all the effects happen together, you would need to do some sort of numerical analysis or program to actually calculate those compressible Navier-Stokes flow problems. But that can be expensive. That can take a lot of time. So this idea of breaking up your compressible gas dynamic flows and just like there's the converging area part and then there's the non-changing area part can get you somewhere, as opposed to just throwing your hands up in the air and saying, I have no idea where to start. So you're really restricted in compressible flow to these very simple problems, right? Anything beyond this involves definite grad school level courses. But with the simple approach, we can write down some relationships, and we can write down some more relationships in order to get Mach relations into the temperatures and pressures. So this is what we're going to do for this section. Next lecture will be this, and then we'll do that. So these are the three tools you have of gas dynamics to lump them together, look at the relationships. And right, you're always sort of going, here's a state 1, here's state 2, right? And then over here, right, you could have state 3 right here. And then over here, right, you could have state 4. So state, 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 and state. So all these equations are relating. If I go from here to here, what's the relationship here? If you knew something about here, now you would know what state 2 is. Same thing, go from here to here, now you would know what state 3 is. Now going from here to here, you could figure out what state 4 is using the Fano or Rayleigh relationships. So that's the motivations of how we use these actual very simple models for extremely hard, difficult problems. Extremely hard and difficult. So there's going to be even more equations thrown at you today, right? Remember before we wrote down the Gibbs equations just related the pressures and the temperatures and the densities, right? Before we wrote down those Gibbs equations, and what did they tell us, right? They told us ratios of temperature at state 1. This ratio is labeled this ratio for a process, something like that, right? So I can relate the temperature at state 2, the temperature at state 1 to the pressures. But this is just states. These are just equilibrium states of things, and they have nothing to do with velocities at all. So the point of what we're doing for this entire lecture is we're trying to arrive at similar types of state relations. And the state relationships we want are, right, kind of the same relationships. And we want them to be functions of our Mach number and the fluid, right? So this relationship, I want to be some sort of function of a Mach relationship number. Remember that Mach is just the velocity you're going divided by the speed of sound. It's a non-dimensional velocity, but you're non-dimensionalizing your velocity by a very special velocity. It's the velocity, it's the fastest that pressure wave can go in the medium it exists in. And this also talks about the medium. Right? So think of, we're going to write relationships for temperature, we're going to write relationships for pressures as well, and even densities. And they're going to be functions, right, of the flow I'm designing for and the medium that's flowing, or the gas. So that's where the flow comes in. So they're really nasty functions. They have all kinds of powers involved in them, but just from a state, you're trying to get from state 1 to state 2. And if you know what the Mach number and the medium that you are, you can actually figure out what the other compared state is. The other difference that we get is instead of just going from arbitrarily from one state to the other state in these flow relationships, we're restricted to actually figuring out stagnation ratios and critical ratios. So you don't have the freedom of just going from any old state to any old state. The functions and relationships we derive are ones that go from stagnation states and critical states. And we'll go more into what those states are later. But that's where we're headed. What on earth is this thing? And we can get to it through simple approximations.